that is equal to 0. So we will get 3 distinct value for lambda, which is equal to say lambda 1 is equal to 0, lambda 2 that is equal to 1, and lambda 3 that is equal to 2. So the matrix A have 3 distinct eigenvalues. Lambda 1 is equal to 0, lambda 2 is equal to 1, and lambda 3 is equal to 2. Our question is to find the eigenvalues and eigenvectors. Till now we have only find the eigenvalues. This is the longest example because now we need to find the eigenvector for each eigenvalue. First of all, we will find the eigenvector for lambda is equal to 0, then we will find the eigenvector for lambda is equal to 1, and then we will find the eigenvector for lambda is equal to 2. Okay, so this is the end of the first part, that is the finding the eigenvalue. Now to find the eigenvector, okay, to find eigenvector, as we discussed in the PPT, that we need to solve the homogeneous system A minus lambda I into x that is equal to 0. Now we have lambda is equal to 0. That is the first case. If we take lambda is equal to 0, then we will get first case for lambda is equal to 0, then A minus lambda I we can find, that is from this one, as we have started in the first one. This is the A minus lambda I. Now if the lambda is equal to 0, then A minus lambda I that is equal to minus 2, minus 8, minus 12, 1, 4, 4, 0, 0, 1. So A minus lambda I into x. So for the lambda is equal to 0, the homogeneous system will be minus 2, minus 8, minus 12, 1, 4, 4, 0, 0, 1 into x that is equal to x1, x2, x3, and that is equal to 0, 0, 0. This is the homogeneous system, and the solution of this homogeneous system will give us the eigenvector. So now we will solve this equation using Gauss elimination method by doing the row operation. For here the we will write here minus 2, minus 8, minus 12, 0, 1, 4, 4, 0, 0, 0, 1, 0. This is as we all know, this is the method of Gauss elimination, right? So now we will use the row operations to find the solution. First of all, I will divide the first row by minus 2. So I will doing the process. R1 becomes R1 into minus 1 by 2. If I divide this row by the minus 1 by 2, then I will get here 1. Okay, so by dividing by minus 1 by 2, I will get this one is equal to 1, 4, 6, 0, here 1, 4, 4, 0, and here 0, 0, 1, 0. Because second row and third row will be same, here I have divided the first row by minus 1 by 2, so minus 2 by 2 that is 1, minus 8 by minus 2 that is 4, minus 12 by minus 2 that is equal to 6. So this is the after this operation. Now if I do the second operation, that is, now I will do R2 becomes R2 minus R1 here. right? So if I do this process, then I will get the first one is same 1 4 6 0. Second one will be here 1 minus 1 0, 4 minus 4 0, 4 minus 6 that is equal to minus 2. This is 0 here 0 0 1 and 0, right? Third row will be the same. So now there is no pivot in the second and the third variable for the second and third variable. So we will take here x2 is equal to k, right? We have no pivot for the second variable. Okay, we have no pivot for x2, so we need to take x2 is equal to any let x2 is equal to t or x2 is equal to k. So here let x2 is equal to k, because here no pivot for the second variable, right? So if we take x2 is equal to k, then from the first one we will get x1 plus 4k plus 6 x3 is equal to 0, and for the third one we will get x3 is equal to 0, right? So that implies the first equation will be x1 plus 4k is equal to 0. So x1 is equal to minus 4k, right? Here x2 is equal to k and x3 is equal to 0. So we have the values of x1, x2 and x3. So now we can say our eigenvector for the lambda is equal to 0. So our eigenvector for lambda is equal to 0, that is x1, x2, x3 is equal to, we have x1 that is equal to minus 4k, x2 that is k, and x3 that is 0. So if we take k common, then here minus 4, 1 and 0. Okay, so eigenvalue for the lambda is equal to 0, that is minus 4, 1 and 0. Okay, so in this way we can find the eigenvalue for any we can find the eigenvector for any given eigenvalue. So if I repeat that, we have started this example from very soon. We have discussed that we need to find the eigenvalue and eigenvector for the matrix this one, right? If you look at here, we have discussed to find the eigenvalue for this matrix. Okay, so we have started with the characteristic equation. By solving this characteristic equation, here we get the values of eigenvalues, that is lambda is equal to 0, lambda is equal to 1 and lambda is equal to 2. And now we need to find the eigenvector for all these eigenvalues. We have 3 eigenvalues, 0, 1 and 2. So we have only find now till we have find the value of eigenvector for only for lambda is equal to 0. In the same way we can find the eigenvector for lambda is equal to 1 and lambda is equal to 2. So this is the in the end this is the eigenvector for lambda is equal to 0, that will be minus 4, 1 and 0. In the same way, if we find the eigenvector, okay, in the same way similarly we can find eigenvectors for lambda is equal to 1 and lambda is equal to 2. So I am not going to find the eigenvector for these two eigenvalues, but this is for the homework, but I am giving you the solution that what will be the eigenvector for lambda is equal to 1 and lambda is equal to 2. For lambda is equal to 1, eigenvector E1, that is equal to k minus 4 0 1. Okay, k belongs to R, right? And for the eigenvalue lambda is equal to 2, the eigenvector E2 will be k minus 2 1 0. K belongs to R, right? As this is two answer for the second eigenvalue and this is for the third eigenvalue. This is the eigenvector for the second one, this is the eigenvector for the third one, and for the first one which we have already found, which is here, that is eigenvector for the eigenvalue 0, that is equal to, we have find k minus 4 1 0. K belongs to R, right? This is the first one, and these two are in homework for the students. You can find in the same way as we have find for the first eigenvalue, you can find for the second one and for the third one. So this is the end of this example. In this way we can find the eigenvalues and eigenvectors of 3 by 3 matrices, right? So these are the some examples of finding eigenvalues and eigenvectors. There are so much for the discussion in this topic of eigenvalues and eigenvectors. Let us quickly discuss some properties of eigenvalues and eigenvectors. So if we look at the PPT, these are some properties of eigenvalues and eigenvectors, because properties are most important in the GTU examination. There are so many examples which are frequently asked, which are based on the properties of eigenvalues and eigenvectors, right? So let us look at the PPT here. Here this is the definition of trace of the matrices, which we have already discussed. This is the property number 1. The sum of the eigenvalues of a matrix equals the trace of the matrix, right? The sum of the eigenvalues of a matrix equal to the trace of the matrix. The second property, a matrix is singular if and only if it has a 0 eigenvalue, which we have already discussed, that if the matrix has a eigenvalue 0, then the matrix is singular. Third property, the eigenvalues of an upper triangular or lower triangular matrix are the elements of the main diagonal. This is the important property for the exam point of view. If in the exam if you ask to find the eigenvalues for the triangular matrix is either upper or lower, so you can directly say that the eigenvalues of any triangular matrix is the elements of its main or the front diagonal, right? So you can easily find directly, you can find the eigenvalues for the triangular matrix. The fourth one, if lambda is an eigenvalue of A and A is inversible matrix, then 1 upon lambda is the eigenvalue for the inverse of A. Okay, this is the simple one. The fifth property is, if lambda is an eigenvalue of A, then k into lambda is an eigenvalue for k into A. This is the also very simple property of eigenvalues. The sixth one, if lambda is an eigenvalue of A, then lambda raised to k is also then lambda raised to k is eigenvalue of the matrix A raised to k for any positive integer k. This is also the second most important properties from the eigenvalue. If you if you ask to find the eigenvalues for a square or a cube, then you just need to find the eigenvalues for a. Then if you want to find the eigenvalue of a square, then you need to square all the eigenvalues which you have find for the matrix A. So if lambda is an eigenvalue of A, then lambda raised to k is an eigenvalue of A raised to k for any positive integer k. If lambda is an eigenvalue of A, then lambda is an eigenvalue of transpose of A. That means if I am taking the transpose of any matrix, then the eigenvalue will be same. Okay, so eigenvalues of A and transpose of A will be equal. In the ninth property, the product of the eigenvalues of a matrix that is equal to the determinant of the matrix, which we have already discussed previous in the for the 2 by 2 matrices. Okay, and here I am discussing one more theorem for the eigenvectors. Eigenvectors corresponding to distinct, that is different eigenvalues, are linearly independent. Okay, this is the next theorem. If lambda is an eigenvalue of algebraic multiplicity k of an n cross n matrix A, then the number of linearly independent eigenvectors of A associated with lambda is given by n minus r into A minus lambda I. So these are some important theorem for the eigenvectors. So the time is going over for this session, but in the next session we will continue with this topic of eigenvalues and eigenvectors. In next time we will solve some example which is based on these theorems and the properties, and then we will discuss the Cayley-Hamilton theorem and the example based on that. So that's it for this session. Thank you very much.